So in this video, we're going to discuss limits at infinity, which is really just answering the question, can a limit exist as x approaches positive or negative infinity? And the answer is sometimes yes. So let's take a look at one particular case. So here we have just some rational function here. And let's just take a few minutes just to graph this and make sure we got this. It's a nice review of stuff we did back in chapter 2. So first thing that we're going to want to find is any vertical asymptotes. And vertical asymptotes is simply where our denominator is equal to 0. And so we can say x is equal to 1. Now we got to see what our horizontal asymptote is. And our horizontal asymptote is, in this case, we would look at the degree of the numerator compared to the degree of the denominator. And here we can see that the degree of the numerator is equal to the degree of the denominator. Therefore, my horizontal asymptote is simply the quotient of the leading coefficients. And so we would say leading coefficients, we got a 1 and a 1 here, so 1 divided by 1. And so we would say that our horizontal asymptote is y is equal to 1. Okay? All right, so don't need to leave that there. You guys got the idea. All right, the next thing, are there any zeros? Well, our zeros are going to be where our numerator is equal to 0, right? So x plus 1 is equal to 0, and x is equal to negative 1. And finally, let's see if there are any y-intercepts. And all that means is we're going to evaluate this function at 0. So when f is equal to 0, 0 plus 1 is 1 over 0 minus 1. So we just get negative 1. So our y-intercept is at 0, negative 1. Okay? So we're going to take this information and let's graph it. So first things first, let's go ahead and graph our vertical asymptote. That's where x is equal to 1. And next, let's go ahead and graph our horizontal asymptote. That's where y is equal to 1. And finally, let's go ahead and graph any zeros. So we got x is equal to negative 1. That means we have a point at negative 1, 0. And we have a y-intercept at 0, negative 1. So we've got a point here. So using that, let's just go ahead and try our best to kind of graph this. So we've got this here, and that means this branch is going to approach this vertical asymptote. And for the other branch, you can just kind of leverage the idea that it's somewhat symmetric. So let's just go ahead and go plug in 2. When x is 2, we get 2 plus 1 over 2 minus 1. So that's just going to be 3. So 2, 3 is going to be a point right over here. Okay. And then from there, let's just go ahead and graph. This is going to go up this way, and this is going to go down this way. All right, so there's our rational function that we've just graphed. So now that we have this graphed, we can use this graph to now answer the question of the following. What is the limit of this function as x approaches infinity? In other words, as x gets really, really large, as x starts to approach infinity, as x is going this way, excuse me, I should probably draw it this way. As x is going this way towards positive infinity, what is happening to our function? Our function looks like it's approaching what y value? It looks like it's getting closer and closer to 1. So let's write that. F of x approaches 1 as x approaches infinity. Okay? So we can see here that our limit as x approaches infinity is exactly where our horizontal asymptote is. Huh. Interesting. All right, let's try to find our limit as x approaches negative infinity. So the limit as x approaches negative infinity, so this time as we're going in this direction towards negative infinity, question is, what's our limit of that? Well, x plus 1 over x minus 1. Well, our function looks like it's approaching also 1, where our horizontal asymptote is. So we can pretty much make the same statement, or pretty similar statement, I should say. Let me just go ahead and write that. F of x approaches 1 as x approaches, in this case, negative infinity. So we can see here there's nothing too complicated about this idea, that all the stuff that we did earlier on with horizontal asymptotes was to give us a good foundation for evaluating limits at infinity for these rational functions. right? So this idea with rational functions, we can say our horizontal asymptote, our line y equals L, right? Which we'll just underline here. Our y equals L is a horizontal asymptote if the limit as x approaches negative infinity is that L value, or the limit as x approaches positive infinity is that L value, right? So all this time we were working with horizontal asymptotes, not really realizing that they actually are limits. They're limits at infinity. Okay, so the horizontal asymptote is where your limit at infinity is. And we can use and leverage horizontal asymptotes to give us information about our limits at infinity. And now would be a good time to also discuss the limits at infinity theorem, which simply says if c is some real number, in other words, if this is some kind of constant, right? Think back to what we know about horizontal asymptotes, or rational functions, excuse me. When our numerator is a constant and our denominator has some x value raised to some power of r, well, the degree of the numerator is less than the degree of the denominator, which means our horizontal asymptote is 0. So this is the limits at infinity theorem is just saying if you've got a constant in the numerator, then you know that your limit at infinity is going to be 0. Why? Because your horizontal asymptote is 0. Okay? All right. So with that all being said, let's try a few practice problems with this. Okay? So we're going to do this without relying on our graphs, although you can definitely look at the graphs of these in Desmos or in your graphing calculator as you go along. But I want us to kind of just think a little bit about what's going on here. So we got the limit of this particular function, and I'm just going to use a limit property just to split this up. I'm going to say the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. And I'm just using a limit property here. Okay, and we reviewed these in previous videos. So the limit as x approaches infinity of 5, well, if my function is 5, it's just some constant. As x gets closer to infinity, it doesn't really matter. This is always going to be equal to 5. Now let's look at this next part, which is the more important part. What is the limit as x approaches infinity of this rational function 2 over x squared? Now, really, I'm going to write something down that you actually shouldn't write, but I'm just going to do this to demonstrate this, and I'll explain why you shouldn't actually write it. The limit as x approaches infinity of 2 over x squared should be thought of really as 2 over infinity squared. And I'm just writing this just to kind of demonstrate this idea. I mean, just ask yourself, infinity squared, well, that's a huge number. That's infinity squared. That's right. 2 over infinity squared, as the denominator is really, really large, we know this by now, that all of this is going to approach 0, right? So a small number divided by a huge number is going to approach 0. Now, why shouldn't I actually write this? Why is this something that's kind of like a faux pas? Well, it's because infinity is not a quantitative value that you could actually directly substitute into a function. You don't evaluate a function at infinity. You really just ask yourself what's happening to the function as x approaches infinity. So this is not something that you actually write. So I'm going to go ahead and scrap it now. But for our intents and purposes, all we really need to say here is just the following. The limit as x approaches infinity of 2 over x squared, well, that's just 0. That's all you really need to write there. So the limit of all this is just going to be equal to 5. Okay? So there's no work that you need to show for actually plugging in infinity. You can just kind of intuitively think about what happens as my denominator gets super large. Well, the whole thing would just get closer and closer to 0. So we would write 0. Okay? All right, let's try another one. Let's look at the limit as x approaches infinity of this function here. Well, real quick, let's just kind of think about the direct substitution here. Just for a second, and I'm going to write this in red because, again, you're not going to actually write this out because, again, you can't plug in infinity. But if you think about this for a second, negative infinity plus 4 over 5 times infinity squared. This makes me feel weird just even writing this out, but hopefully this kind of hammers a few things home. Negative infinity plus 4, well, that's still going to be negative infinity. Well, infinity squared plus 2 times infinity, all of this, regardless, is going to be infinity. This is, I'm just showing this just to indicate that this is another indeterminate form that we should be aware of, right? Doesn't mean that the limit doesn't exist. It just simply means we cannot evaluate the limit with the information that we're given right now. We've got to do something else to the function. So we've done this a couple times now. So let's write an equivalent limit statement. So the limit as x approaches infinity is negative x plus 4 over 5x squared plus 2x. And let's just go ahead and divide each term by the highest power of x in the denominator. All right. So this is a common technique that's going to be used when you're dealing with rational functions and you're trying to find a horizontal asymptote. Find the highest power of x in the denominator, in this case, the denominator. And we're going to divide everything, and I'll just write this in orange. We're going to divide everything by x squared. So one way of just writing that is just multiplying everything by 1 over x squared. But we're going to divide everything here by x squared. I'll just write this note out here. We're going to divide each term by the highest power of x. And why are we doing this? Because this is our way of applying the limits at infinity theorem, right? Because we know that if we can rewrite this with a constant in the numerator and x squared in the denominator, this effectively each term will effectively become 0, where that is the case. Here's what I mean. Let's actually divide by 0, and hopefully that'll make more sense. So the limit as x approaches infinity, okay? If I divide negative x by x squared, what is that? Negative x over x squared is negative 1 over x plus 4 divided by x squared, is just 4 over x squared. Now let's take care of the denominator. 5x squared divided by x squared is just 5. And 2x divided by x squared is 2 over x. Well, if I'm finding the limit at infinity, using the limits at infinity theorem, let's think about what's happening as I find the limit of each of these terms. What is the limit of negative 1 over x as x approaches infinity? Well, that's just effectively 0. What is the limit of 4 over x squared as x approaches infinity? Again, that's 0. Now in the denominator, we have 5. And again, apply the limits at infinity theorem. The limit as x approaches infinity of 2 over x as x approaches infinity, that effectively becomes 0. So all of this tells us we just have 0 here. Okay, and we're showing the work to really make sure that we understand where this comes from, but you probably could have figured out very early on, just by looking at that original function, that our limit was going to be equal to 0. Can you figure out how? Yep. Note, the degree of the numerator, in this case, was less than the degree of our denominator. That means our horizontal asymptote was going to be y equals 0. And that's confirmed there. But this process of applying the limits at infinity theorem is going to be a very useful one. So you want to definitely have that in your pocket as you move forward. So there's some practice problems on the back page, which I'll let you guys try, and I'll go ahead and post my solution.